Hi guys, thank you for having me up here today. So I'm excited to be able to share this project with you. One of the things that you'll notice is absent in that bio is, a knowledge of really the building envelope components of all this stuff. So you guys in a lot of ways are experts that I am here to learn from. But today I want to tell you about an exciting project that I'm working on. So one of the things that Passive House really excels in, that we just heard about in the last two presentations, is helping us not just create new buildings that are fantastic, but to adapt our existing building stock. So by 2030, if we were to only and this is a couple years old, this stat now, if we were only to address new construction, we would still have 70% of our building stock left as significant liabilities in the existing building market. So having to get better technology into these existing buildings is really part of the challenge. And in particular in Canada, we have a lot of post-war apartment towers, these lovely brutalist structural concrete buildings. Typical features include balconies that are cast in concrete that spans through the thermal envelope and then creates a fin on the exterior of the building. As we're building these in Chicago today, but we as Canadians have a huge amount of these buildings to try and adapt. So the challenges in these buildings, deteriorating envelopes, no insulation, poor continuity of insulation when the insulation exists, mold, lots of hazardous materials, asbestos throughout, mostly non-friable, which makes it easier to deal with, but still there, lack of thermal control, and end-of-life systems. So when we think about buildings in the 1970s, they're all sitting at that lovely 40-year mark, which is when just about everything in the building should have been replaced already or has been replaced once and is coming up for a second round. So, and the last challenge, of course, is that a lot of these buildings have people in them. So the project team that we're working with, ERA architects are really the leaders on this project, and we were lucky enough to join them. We're working with Solar out of Germany, so we tried to bring on somebody who really knew how to do this at the large scale. Intuitive, Reinbold, and our partners, Nemetz, who are electrical, JMV Consulting, and then of course our client is City Housing Hamilton. So City Housing Hamilton has a $1 billion portfolio, and they're really committed to Passive House as a standard moving forward. They are hoping with this particular project to lead harbor revitalization, West Harbor revitalization. It will be the first of 7 Passive House projects in the city, and they're trying to make this replicable. So the technologies that we're putting forward in this project, we want to be able to share. So this is the project. It's 18 stories tall. It's got this beautiful lake view. And it actually has a 3-story building next to it, which is much more like existing buildings that you might have in this part of the world, right? So we're going to be able to look at low-rise and high-rise, both as retrofit technologies, all part 3. So it's going to be EnerPHit certified. The intention is a 30-year asset renewal. Just about everything in the building needs to be replaced. And when we're done, we hope to have 146 new rental units for seniors. So the project is being financed through not just integrated capital planning, taking all of the money they intended to spend for the next 10 years and combining it and bringing it forward with the intention of paying for the loan with the savings on the operations costs from having this very low energy asset when we're done, along with loans from the Federation of Canadian Municipalities and from the CMHC. So one of the things that makes this especially challenging, it's their first Passive House project and has to be certified to get this funding. So what are we going to be doing to these buildings? We're going to do an R38 overcladding with Passive House windows. And to deal with that thermal bridging at the balconies, we've decided to get rid of them. So we're going to chop the balconies off, overclad, and replace them with Juliet balconies. At the mechanical level, we're doing a centralized HVAC system with cooling, with a high-performance ERV located on the roof. And the reason we went that way is that the building in its current form has shafts which contain both exhaust and supply, serving all of the suites already. So instead of having to make another 300 holes in the building envelope, we decided to try and go centralized. We're going to be putting sprinklers in. Combustibility is a huge issue in high-rise towers and multi-unit residential. And then from a modernization perspective, we're going to be doing new kitchens, new cabinets, accessibility upgrades. A full quarter of the suites going in are going to be fully accessible, along with a new community room. So I think I alluded to this. Challenge number one, thermal envelope continuity. So what we've got from a starting point has got a lot of thermal fins on it. And our strategy for dealing with that is to make it smoother. From a mechanical perspective, in a typical passive house, you can put a gutter on the building and drain the water down the outside. For this building, our rainwater leaders currently run in the inside of the building. So that's 18 stories worth of cast iron drain that we have to somehow insulate. If we try and run it on the outside of the building, then we introduce potential ice dam issues. So we could destroy that exterior rainwater leader. So our current strategy is this really neat backwater valve, which is normally closed and will only open when water goes through it. So we should be able to eliminate at least air movement through our rainwater leaders, and then we're going to try and only insulate the top 2 stories. For the for the roof drains, I've written storm drains, I apologize. Sanitary drains, it should read right over here. For our sanitary drains, we have ventilation at the top, and so those vent stacks also allow cold air into the building. So we're going to be using an air admittance valve at the top of each stack to keep cold air from running down those ventilation stacks. So at the mechanical level, it's how we're trying to deal with these sort of major Part 3 systems and keep cold air out of the building. From a ventilation perspective, we're going to be doing a full integrated HRV system. So one of the challenges that we've encountered thus far is there's a very limited selection of Passive House certified ERVs in North America. There are a lot that meet the standard, very few who have gone through the certification process. So we're currently working with Canadian manufacturers who are over 85% or over 90%, and trying to secure one who wants to pursue the Passive House certification. And our backup is a Swagon unit, which is already carrying that certification. So when we first got the project, we were thinking we were going to use typical small ERVs. One of the challenges we quickly found was that at 250 square feet to 300 square feet per suite, so these are almost all bachelors, there's very few ERVs, even in the Passive House field, that are small enough and have high enough efficiency. Another challenge that existed with fully compartmentalized systems was that we wanted to provide everyone with their own domestic potable water heating system, but the only ones that were available were electric. So we ended up with sort of individual electric resistance heat providing the top up. Now, we've talked about the fact that these buildings are 90% more efficient than a typical building, but with low-income housing, we're still trying to think about giving people an energy source for their heating that is as cost-effective as possible. So we wanted to go to a heat pump system rather than an electric resistance heater. So that drove us to a centralized system where we were able to decouple the domestic water heating, which was sort of initially intended to heat the ERV air after it came through, and went to a centralized system. So with a centralized system, we also get the benefit of being able to provide cooling. And we're going to be controlling both the cooling and heating and the ventilation airflow. Instead of having an individual system, we're actually going to be providing everyone with a variable volume damper with modern controls. So they will be able to set it to both a heating or a cooling mode or to a ventilation override mode. So we should have more ventilation available if they want, and then a low ventilation rate that's standard throughout the day. We're reusing ductwork. The ductwork, we think, is currently got a leakage rate of about 25%. so that's a lot. We have therefore undertaken an investigation into how to reuse this ductwork rather than removing it. So what we've learned is that there are 3 major technologies. We can use locally applied aerosols. So there's actually little robots, and they run around inside the ductwork and apply a mastic, spray applied on the inside. We can, of course, do a traditional taping process, but it would require removing all of the fire barriers around these exhaust ducts, so it's going to be quite intensive. And the last one is a technology called AeroSeal. So that was developed by research facilities in the States, and it is a polyvinyl chloride substance that only adheres to leaks in the ducts. So it doesn't coat the duct and it doesn't remain in the system, but it can eventually accumulate in any leak and block something up to 3/8 of an inch. So there's been recent research coming out of Minnesota that says that this is effective for eliminating leaks up to 85% of the original. So these are the technologies that we're going to be looking at to try and improve the performance of this system without necessarily having to replace all of it. Another challenge at this multi-unit residential level compared to sort of the individual housing level is that when we followed the ASHRAE 62.2 2016 code, which is the requirement in Part 3, we found that we had 17% more required ventilation than the passive house calculations by our passive house consultant. So from an energy perspective, that was a little interesting. So looking at, and then if we follow ASHRAE 62.1, which is the other option, we were 5% above that even. So one of the things that we realized as we were looking at the research was that more research shows that more ventilation is better, even in a passive house. And one of the reasons that is that as humans, we are a key source of contaminants in our own spaces. So especially in a small suite, CO2, which we breathe out, actually is a contaminant of concern. So if we don't dilute it enough, then it has impacts on our health and well-being. Over here, I've got the impact of carbon dioxide on human decision-making. So it actually shows that when you lock a bunch of executives in a boardroom with a bad HVAC system, they make some of the worst decisions that humans can possibly have. I know it explains so much. So I want to make our passive house not that. So we've decided to actually, instead of trying to figure out how we can go with a passive house level, we're going to try and make up for it in other areas of our energy performance and just design for these higher rates. And that's where that VAV box really shines. We can actually design for everyday performance at the low levels, but provide people with manual overrides to get to those higher levels whenever they would like more fresh air. The other thing that we've been thinking about in the passive house system is that we have plans for a recirculating range hood. And we are continuing with that because it's required to be able to get these really tight, airtight buildings. But we also are conscious that cooking in and of itself generates contaminants which are poorly controlled by recirculating range hoods. So if you were to put a natural gas appliance in a passive house, you would be generating nitrogen dioxide, carbon monoxide, particulate matter, and formaldehyde. So that's easy, don't. But you probably still need to cook, right? So induction burners are pretty good electric coils, exist in your toaster ovens and in your toasters, and they release fine and ultrafine particles. And then actually, every time you burn rice by accident, you've also got acrylane polycyclic aromatic hydrocarbons and more particulate matter. So the better your hood is at capturing cooking effluent, the more will be removed from your space. If it recirculates, you're only getting a capture and removal rate of about 50%. So this is another reason that we're excited about having those higher ventilation rates accessible to the folk in our suites, and why we are renovating to increase the amount of exhaust. So instead of only exhausting from the bathrooms, the way the buildings were initially designed, we're exhausting from both the bathroom and the kitchen. Challenge number 3, preventing overheating. So our German consultants are amazing and really experts in their fields. And they did this study where they looked at 5 different options for our building. A base case, internal blinds with active cooling. So this was the only option where we looked at active cooling. And then fixed external geometry and external blinds. And they found that in 4 of these cases, the temperature inside the building in Hamilton was going to be sufficient for human comfort, both today and in a 2040, 2050 weather condition. Now, by 2040 or 2050, Hamilton has a climate analog of Washington, D.C. So that's a really interesting finding, and I was really excited about it. And then I looked over at them and I said, wait, did you look at humidity? And they said, why would we look at humidity? And then they came back about 3 hours later and said, we need cooling. So the thing that we learned from that is that Passive House is an amazing standard, and we need more pieces of equipment that can deal with dehumidification. Because in Ontario, humidity is going to be a bigger challenge than active cooling. So we're adding active cooling to this building. We only need the dehumidification. We don't really need the temperature control. We're going to get both because there's not a lot of really good pieces of equipment that can do dehum without doing active cooling. So stay tuned, and or if you know anyone developing a good tech, let me know. Finally, carbon emissions. So one of the things that we discovered in doing our EnerFit calculations was that the standard is currently neutral as to whether or not we use a natural gas boiler or a heat pump in our major energy generating device. So on our energy recovery ventilator on the roof, once we've recovered as much energy as possible, then we're going to boost the temperature of that air with an active source. And we have a funding incentive that's tied to achieving an EnerFit certification, not to reducing our carbon emission. So we're currently in this compromised position where we would like to put a heat pump in and we're carrying that, but we have sort of a budget of about $17 million. This is about $100,000 per suite, which sounds like a lot of money, but we've used it up pretty quickly. So some of the challenges that we've identified using the Passive House standard in particular was that they're actually looking at a national rate for carbon. So they're not acknowledging for us, even in that sort of Passive House carbon calculation, we didn't seem to be getting as much credit as we expected for that very low Ontario grid emission rate for our hydro. And then sort of thinking about whether or not that's fair, thinking about the electrons that we're using within the Ontario market and whether any of those came across the grid from Quebec, whether any of them really were originating in Calgary. And I put up this graph just because I love it. This is where we are today in terms of emissions from our electricity grid. And these are a bunch of projections by various sort of authoritative sources, the IESO, the National Energy Board, and Ontario Power Generation, about where the emissions might go. So the other challenge with going to heat pumps is trying to understand whether or not we're putting a lot of extra money into the system that is really supporting an energy source that's going to remain very clean. So in addition to all of these energy goals and creating a building that will hopefully be low cost to operate and comfortable, we're trying to make this building fit into the community effectively and support the occupants in ways that the previous building didn't. So the new building is going to include outdoor seating areas. There's a new solarium going up on the top floor, so they'll have a community room that overlooks the lake, and that's accessible for other members of the community to hopefully help engage people further into that building. And with those modifications, there's also a little green roof going on. The building should fit more effectively into the fabric of the city. And